several review points on connections in parallel, connections in series, and a specific homework problem. So this will be the homework problem I'm going to talk about. I will not use any numbers. I will use just general algebraic analysis. What we see here is elements connected in parallel and in series. So let's review first properties of those wiring. Series. That's what it means. Several elements connected in such a way that electric current traveling through each is the same. If it's not the case, it's not in series. It means no junctions, no splitting points. You see a splitting point, that's not in series. What elements does not matter. Could have been a resistor, could have been a battery, does not matter absolutely. What about voltage? They might have different voltage. But what is voltage? Voltage is potential difference at every specific point. There is specific potential, potential 1, potential 2, potential 3, potential 4, potential 5, and voltage is the difference. Mathematical difference. Well, in my case, if electric current travels to the right, and as we know, electric current always travels from, well, through a resistor, always travels from high to low potential. So I know that V1 is higher than V2. This is a positive difference, and delta V2, well, that's EMF if I have a battery there, but still it's going to be equal to V2 minus V3, and delta V3 will be equal to V3 minus V4, and delta V4 will be equal to V4 minus V5, and if you add them up all together, voltage 1, voltage 2, voltage 3, voltage 4, etc., etc. What do we get? V1 minus V2 plus V2 minus V3 plus V3 minus V4 plus V4 minus V5, and what's in the end? V1 minus V5, which is the total voltage across this whole wiring, delta V total. That's how it works. And of course, for each element, one, two, three, four, for each element you can write a law. Well, what law can you write for the element number 1? Technically, we could have used this subscript, but electric current is the same, so we don't have to. But these variables are related. Delta V1, which is again V1 minus V2, is equal to I1 times R1 or I times R1. What law can I write for the... this is 3, this is 4. Yeah. So same for 3, 3, same for 4, 4. What law can I write for a second element? Well, EMF is just equal to this difference V2 minus V3. Nothing else. And if those resistors would have been bulbs, we could calculate the power. How? Power for each element is equal to this product, which is equal to this product or this ratio and highest power means brightest bulb. That's it. Power is bulb. Brightness. Brightness is power. Knowledge is power as well, but brightness also is power. Okay. What about elements connected in parallel? 1, 2, 3, 4, etc., etc. And again, the nature of this element does not matter. It could have been a resistor, could have been a battery, another resistor, or another battery, but we have not covered circuits with 2 batteries, so don't worry about that. What do we know about this situation? The voltage has to be the same. If it's not the case, that's not a parallel connection. What is it equal to? Well, of course, there's electric potential, V1, V2, which is higher, which is lower. For that, we need to know how electric current travels. Let's say this battery has a positive electrode here and a negative electrode there. In that case, okay, let's remember again. Through a passive element, electric current travels from high to low potential. But through a battery, as we know, there are tiny demons that make electrons move against the force. Inside the battery, electric current travels... Oops, sorry. Inside the battery, electric current travels from low to high. Outside of the battery, electric current travels from high to low and comes back. But inside the battery, it travels from low to high. So here, electric current should travel that way, that way, that way, that way. I1, I2, I3, I4. And of course, the law of conservation of charge says if we add them up, I1, I2, I3, I4, we should get the total current traveling where? Well, we don't know what's there, so we can say there. What we could actually say, if we replace this whole system with only, well, well, something else. Could have been something else, I don't know. So, in that case, that electric current would travel through that something else. I don't know what it is. Well, this is just a law of conservation of charge. This is what we call the junction rule. And of course, for each element, we can write the Ohm's law. Again, for the battery, what does it say? It says now V2 will be higher than V1. So V2 minus V1, and the same voltage V2 minus V1 should be equal to what? Should be equal to I1 times R1 or I2 times R2, oops, sorry, 3, or I4 times R4. We're applying the same law to different elements. And what else do we know? Well, we know if we want to, we could replace resistors. Come on. Okay, let me be ready. We could replace resistors, only resistors, with one equivalent resistor. This equivalent resistance would be equal to just sum. To prove it, we have to use these laws. And what we know here is that in this situation, we could replace these three resistors with one equivalent resistor. And for that, we would have to do this 1 over R1 plus 1 over R2 plus 1 over R3. I just don't have much space here, so I have to fit it in. These are just rules. All right. And again, the power, well, in this situation, of course we could write all three expressions, but the best one is this. Why? Because you can immediately say something about the power if you know resistance, because voltage is the same R will mean same power, and that will mean same brightness. In this situation, this is the best equation to relate brightness or power, because the current is the same. We don't need to carry out that subscript. In this situation, everything depends on resistance. More power, brighter bulb. However, sometimes when a circuit has identical bulbs, doesn't really matter. What you see is I write exactly the same letter again and again and again, R, R, R. So as long as resistance is the same, two equations could be used, because now, well, of course it should be written for each element individually, P1, P2, P3, P4, P5. But now, if resistance is the same, everything depends on either a current or a voltage. For example, I can immediately say that the bulb number 1 will be brighter than the bulb number 2. Why? Because it has a higher current, electric current, let's say it travels to the right, electric current I1, then splits, so electric current I2 has only part of I1, so it's less. And if I use this equation, same R, less current, less power, dimmer bulb. What else can I say immediately? Well, I can say, so what did I say? Say that brightness 1 is more than brightness 2. Okay, I can say that brightness 4 is more than brightness 2 again. Why? Because of the voltage. Now I don't care about current, what I care about voltage. This voltage, delta V4, now splits. And we know for identical bulbs it splits evenly, but even that does not matter for brightness. Even if it wouldn't split evenly, still it splits. The voltage number 2 is less than the voltage number 4, so power number 2 is less than the power number 4, and that means brightness also is less. So, but in this particular case, this voltage will be a half of 4, and this will be a half of the voltage number 4. Now, how do I know this? Well, it's a good exercise to analyze your connections, specific connections, when you have identical elements, R, 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 you know, and see what's going to happen. Now that problem. So we've got a battery. First we've got two identical resistors. Then we have two different resistors, but one is 3 times of another one. All right. We know what to do. Minus, plus. So this total voltage equals EMF. However, as I just said, we know for sure for two identical elements, this total voltage splits in half. These are voltages, not potentials. And I know for sure that now for other bulbs the same voltage splits, but not evenly. Again, electric current I, which travels through the battery, then will split into electric current I1 and I2. And delta V1, delta V2, delta V1 should be equal to what? I1 times R. Delta V2 should be equal to what? Same current I1 times R, because they're connected in series. And that is why delta V1 is equal to delta V2. But delta V1 plus delta V2 should be equal to EMF. So 2 times delta V1 is EMF. And that's how we know it's a half. And now I can write delta V3, delta V4. I know that I can see it immediately that delta V3 should be equal to 3 times of delta V4, because the resistance is 3 times. Well, but let's prove it again as an exercise. Delta V3 should be equal to I2 times 3R and delta V4 should be equal to same I2 times R. And now you can see why this one is 3 times of this one. Or else do I know? I know that if I add them up together, delta V3 plus delta V4 should be equal to what? The same EMF. Because now what we see is elements connected in parallel. This point, this point, this point, this point, this point, they all have the same potential. This, they all have the same potential. So EMF, but as we just said, 3 of delta V4 plus delta V4 equals EMF. So 4 delta V4 equals EMF. That means EMF over 4 gives me delta V4, or EMF over 4 times 3 gives me delta V3. If you knew numbers, you could calculate each voltage. Okay, finish this. Delta V1 equals EMF over 2. Now what do we know? Well, everything. For example, if these would have been bulbs, you could rank voltages based on their values. So delta V1 equals delta V2, and they are EMF over 2. And delta V3 will be higher, so they'll less than delta V3, because it's over 4 times 3.75, and this is 0.2, but they all will be higher than delta V4, and delta come on, work. Delta, so my computer is dying, delta V4. So, same brightness ranking, brightness 3, brightness 2, and 1 will be the same. And the dimmest will be 4. If these would have been bulbs, of course. If. But what else can we know? Potentials. Of course, this potential is set to 0. So this potential is 0. This potential is 0. Now, how does current travel? Current travels, again, inside the battery from low to high, outside the battery from high to low, from high to low. And we know that electric potential drops in direction of the current through a resistor, through a passive element. So it drops here. This potential equals EMF, so it drops here to EMF minus voltage, minus a half of it. Or it rises here from 0 to a half of EMF, rises here. Alright, what's happening here? This potential will be equal to what? Well, potential drops from potential at the top, EMF, by what value? By value of delta V3, which is 3/4 of EMF. So this will be this potential. Of course, it will be equal to 1/4, because this potential also should be higher by 1/4 by delta V4. And this is how it's done.